Start module 6 now, chapter 6, if we go along with my textbook. And that's on optimal estimation. We're going to kind of go through optimal estimation by how much we assume about probability and probability distributions. So we'll start with least squares, which doesn't assume anything about probability. There's no probability in least squares. But what we're going to start doing is using matrix in the language of matrices to go about doing a lot of this stuff. So we can use least squares as a way of introducing optimizing, where we use a lot of matrix arithmetic and calculus. So let's start with this measurement model. And we got this in our state space in module 5. Z equals hx plus v. Z is the measurement. X is what you're trying to estimate. And v is some error. And we'll define what the error is. It's in a second. It's going to be, it's not something out of a probability. It's not a random process or a random variable. But these things are appropriately sized. Z, X, and V are, at least in general, vectors, vectors. And H is an appropriately sized matrix. Here's an example where X is just constant, just a single constant. We don't know, but we take K measurements of it. So we actually have K equations that look like this. But in matrix form, it's going to look like this. And here's what all those terms mean. The H matrix is just this column of all ones. And you can see that just equals a bunch of X's. So that this matrix equation, or actually this matrix equation, corresponds to K of these scalar equations. Let's get some language and notation. This hat means the estimate of something. So X hat is the estimate of X. Z hat is the estimated measurement, or kind of what we expected to measure. E is this error. It's the difference between what we actually measured and what we expected to measure. Which in terms of the state model, it's this. C minus this hx hat. A cost function. We're going to need a cost function because we want to minimize errors. So we'll define it this way. It's this vector transposed times itself. I'm going to say that's the sum of the squared errors. I'll show an example of that on the next chart. So here's another way to state what that cost function is. So here we have our cost function. We'll talk about how to minimize something, minimize that cost function in another chart or so. But let me first show an example that this really is the sum of the squared errors. If we take that example of X is just a constant, but we measure it K times. Here's what the actual measurements are. Here's what that hx hat is. It's this vector of our estimates of x's. Here's what those errors are. It's the first measurement minus our estimate of it, second measurement minus our estimate of it, etc. All these errors. Convince yourself that cost function, which equals this, is this little matrix multiply. And when you do that matrix multiplication, you get the sum of the squared errors. And now let's talk about how do we go about minimizing this thing. And we're going to need some matrix arithmetic and calculus. First, a little bit of arithmetic. If you want the transpose of a sum of matrices, it's just the sum of their transpose. But if you want the product, transpose of a product, reverse the order of that multiplication and take those individual transposes. P transpose, B transpose, A. Remember, matrix multiplication is not commutative. Okay, so let's say we have y, which is a scalar, but it's a function of many variables. We can call those many variables a vector of variables. So x now is a vector, a bunch of variables, n here. What do these things mean? What's this sort of first derivative of y with respect to x, where x is now a vector? Well, it's this vector of first derivatives. What is this second derivative of a scalar with respect to the vector? We define it as this thing called the Hessian, or at least sometimes called the Hessian. Some textbooks call the determinant of that thing the Hessian. We'll just say this matrix is the Hessian. And here's what it means. It's a matrix where the elements are derivatives. The conditions for minimizing this scalar y. Necessary condition is that that first derivative equals 0, which means the vector of all zeros. A sufficient condition is that same first derivative equals 0, but also this second derivative, the Hessian, must be positive definite, which means the determinant is strictly positive and its trace is also strictly positive. Trace is the sum of the main diagonal elements. For the determinant, you got to go back to my MMA course. Pretty basic matrix stuff. So then, okay, how do we minimize, in this case, that cost function that we had for least squares? Here was the cost function. First, I'll take this transpose. That'll be Z transpose minus, I got to reverse this order. It'll be X hat transpose, H transpose. This stays the same. Now I can multiply this out like you did in high school. So it'll be Z transpose Z minus Z transpose this HX hat minus this times Z. And remember, we have to maintain the order of that multiplication. And then finally, minus and minus, so a plus this X hat transpose, H transpose, H. So here we just multiplied all those terms. That necessary condition, we have to take, we're taking the partial of J, which is a scalar function with respect to a vector. So we have, and we want to set it to 0, so we have to take all the those first partials of all these terms with respect to x, set it to 0. So we need a little bit more matrix arithmetic. The first partial of a product like this, either with respect to x, either the x transpose y or y transpose x, is just y. And if the second, this first partial of this sort of squared term, where if this q is symmetric, is QQX, kind of like scalar, but the q had to be symmetric. So we'll just put those on a formula sheet and we'll use them next. So that thing, take my word for it, it's a very simple proof that this H transpose H is going to be a symmetric matrix. So that's going to act like that Q in that formula. This partial of Z, it doesn't have any X in it. We're taking the partial with respect to X hat. This doesn't have any X hat in it, so that's 0. This guy has an X hat in it, and this guy has an X hat in it. over here, go back to that formula. We're using these two formulas, and you get that. And then this is like that x hat transpose qx, or x transpose qx. So we get 2q, where q is now h transpose h. So that's all that stuff, and it has to equal 0. So this is the first partial with respect to x hat, and it has to equal 0. So we get this relationship. The second partial, let's see, no x hat, no x hat. It's only this term, and we use that first formula again, which says that Hessian is just this. You can express it this way. And for now, we'll assume that that thing is strictly positive and invertible. I guess this doesn't really mean it means that Hessian is positive definite. This is the Hessian, and by greater than 0, we mean positive definite. If you assume that, it means we pass the second order conditions, and we can solve this guy. We can take the inverse of this HT. And here is our formula for least squares. Given a bunch of measurements in that H, we found our estimate of X. This thing basically is going to be true if the H is not all zeros and the rank of H is greater than the number of things we're trying to estimate. I didn't emphasize the second order conditions when I taught this course. I usually said it was okay to assume they're satisfied. We'll talk about that in a minute. Let me quickly go over the example that we had where we're just estimating a constant. Here was the H. This transpose H is then this all ones times all ones, which is a sum of ones up to K. That's how many measurements we took. So it's just a number. In this case, the Hessian is just a number. And it's strictly positive. So it has an inverse. So everything's good with this Hessian. And you crank out the formula here, do what all this matrix arithmetic, multiplication, and inverses are. It just says it's the mean. Okay, so far. So that's as far as I'll get for now. But that introduces matrices, cost functions, matrix arithmetic, calculus, minimizing stuff involving matrices. So we're going to be doing more of that.